Welcome to Network Engineering, Chapter 3, the Transport Layer, where we take a look at kind of a general introduction to the transport layer. So the transport layer is that part of the system that provides logical communications between two different applications. And the term logical here means that the actual implementation of the transport layer is transparent to the application. The application reads and writes data to the transport layer, and somehow, whether it be by black magic or sheer luck, data gets to the remote side and back again, right? So different kinds of transport layers are going to have different kinds of properties, but our goal is that the application developer doesn't have to worry about those. So when we talked about the application layer over here in the OSI model, or in that 5-layer internet model, we had talked about sockets. And the socket has data coming in and data coming out, right? And somehow the transport layer is going to allow for the implementation of those sockets, and the programmer isn't going to have to worry about what happens, for instance, if a packet gets lost, or it becomes slow, or there's a new route established. So again, we're hoping to get that insulation between the underlying network and then the layer below. So in the layer below, the transport protocol is going to basically be agnostic from everything beneath of it. So for instance, we're going to see UDP and TCP, two different types of transport protocols. And it turns out that we can run TCP and UDP over just about any kind of lower level network. Like there's nothing that says that it has to be IP over wires. It could be IP over a wireless link, right? So independent of the media layers and independent of the applications above it. The one thing that we have to keep in mind is that we are only implementing a transport layer in the application devices, the endpoints, not on the network devices themselves. So when I look at a device such as a switch, or a switch is going to operate down in this level, most routers are going to operate up in this level, and some could theoretically look at transport layers as well, but they typically don't. So we talk about this being layer 4, we're pretty close to application level. So that's where we are in the transport layer. We still haven't really talked about exactly what the transport layer is supposed to do. So the transport layer is supposed to move data from an application into the lower level network stack or back again. And there's a couple of different approaches that we can take. The two most common are TCP and UDP, and these are part of the Internet Protocol, or IP. And IP is the network link right here. So IP is at layer 3. So the TCP and UDP protocols that we're going to look at are designed to live on top of IP. But it doesn't mean that that's the only protocol that they can operate on, right? That's just the one that they are designed for. And there could be other layer 4 layers above IP. We're just not going to worry about them. So TCP. TCP is the transmission control protocol, and it's a reliable connection-oriented service, and its protocol data unit is called the segment. The UDP is an unreliable, connectionless service whose protocol data unit is usually called a datagram, but for the purposes of consistency, it could also just be a segment. So why would we want to use an unreliable connectionless service? Well, the cost of implementing all of this, and I don't mean like dollars and cents cost. Typically, we're talking about time and resources cost, is much higher in the case of TCP than it is in UDP. So UDP is far simpler and it's very lightweight. TCP puts much more of a burden on the hosts, the servers, to track the connections, the states of those connections, the packets that have been exchanged and whether they've been received or not, to ensure reliability, to make sure that we haven't lost any data. And that adds time or latency. And because it affects latency, it could also affect performance. In other words, there's more overhead in TCP than there is in UDP. Well, then why don't we just use UDP for everything? Well, we're going to find that UDP shifts the burden of getting reliability onto the application. And so sometimes those choices just aren't right. So before we get too far into UDP, let's remember here that TCP provides the following services. First, it provides a reliable data transfer transfer of data. So data is either delivered and received, or an error is, or we get an error back. So when I transmit data to some remote system, I get a ticket back that basically says the receiver has my data and whatever they're going to do with it, they've done with it. I do not get that with UDP. So, nope. When I send something with UDP, UDP may it'll do its best job to deliver it, but there's no guarantee that it actually got to the remote side, and I won't know that it got to the remote side or not. So I assume that if I send data that it got there, but maybe not. TCP has a service called flow control or congestion control. And the idea here is that TCP isn't going to flood the network with data. And that's almost going to guarantee then that the data doesn't arrive to the remote side. And in fact, TCP will send a burst of data, and then we'll see later on where it just kind of waits for some acknowledgments to come back and that the data was received. Huzzah! But until those come back, TCP won't send any more data, and that allows the link to be relatively congestion free. In other words, we don't overwhelm any device along the way. UDP does not do that. I could send out 1 million UDP packets as fast as I can in source code, and I may not be able to deliver them to the hardware that fast, but I can still make those function calls. I can still throw data at the TCP or the UDP layer, and they'll just get dropped. And so, not reliable. Sequence and order delivery. So when we will find when we're sending data out over the network links is that they could get out of order. If I send 2 packets of data and one goes down one route and the other goes down the other route, they're going to arrive at different times, and the one that I sent last might arrive first. TCP will put them back into the right order for delivery. UDP does not. If I send 2 packets with UDP, they could arrive in any order. So if I send packet 0, then packet 1 in UDP, I could receive packet 1 and packet 0 later, or not at all. So there's a big difference between the two. TCP uses acknowledgement messages to let us know that the data got there. That's part of how it implements reliable data transfer. UDP does not. There are timers that wait to find out how long it is since I've sent the message until I've gotten the acknowledgement. And if the timer expires, then we just assume that the data didn't get there. UDP does not. Now, it doesn't mean that UDP can't. It's just that as a layer itself, it doesn't do that. But applications can take over that role if they wanted to. So one of the big advantages of UDP is its simplicity and low overhead. So take a look at the UDP packet header. This is going to be wrapped around the data. So let's say the application puts in some number of bytes. So that's the app data. What UDP is going to do is it's going to add this prefix, this header. And that's going to be added onto the data message. And then later on, the IP header gets tacked on to the front of that. But that's not today's discussion. So how big is this UDP header? Well, these are bits. So the source port is 16-bit or 2 bytes. The destination port is 2 bytes. The length is 2 bytes. The checksum is 2 bytes. That's it, 4 bytes. Sorry, 8 bytes. So the header is 8 bytes for UDP. It's tiny. Later on, when we take a look in detail in part 2, TCP, the TCP header is quite a bit larger. Furthermore, the UDP header doesn't have a lot of information in it. It's going to store the sender's port number, the destination port number, the length of the whole message, the UDP message, and then this checksum is another integer that's just used for error checking. So there's not a lot of other like options or fancy things that we can do here as we can with TCP. So really this is just a lightweight, fast protocol. Simplicity is baked in from the very beginning. One thing that TCP and UDP both allow us to do is this technique called multiplexing. And in multiplexing, and we've seen this term in comp.org. So in comp.org, you saw multiplexers that were often drawn like that. We had a couple inputs coming in and an output and then a selection line. That is one kind of mux, but this is another idea of the same general idea. But in this case, we're reusing the term to come up with an idea where we can allow a single computer to support multiple services. So for example, we have a server in our department named Sloop. Sloop has one IP address, and it can have a bunch of different servers coming in. So for example, it could run a web server, it runs SSH, it might run mail, so that's SMTP. And how does Sloop know when an incoming connection is meant for the web server or the SSH server or the SMTP server? Well, it uses a port number that is attached, that's stored in the header of the protocol. So for example, the web is typically either 80 or 443. SSH is 22, SMTP is 25. So if we just go back a slide, for example, if I were to use UDP to send a message from, say, my computer to Sloop, the IP header, which we don't show here, remember that's a different layer, that's going to have my address and Sloop's address. So that's going to pick the two machines. It's going to say my machine wants to talk to Sloop. But then for my computer to talk to Sloop over SSH, I'm going to have some port number that's kind of randomly assigned. And then we're going to pick port 22. And then I'm going to send a message of some length n and then whatever this checksum is. But it's this destination port and the source port that we can use to uniquely identify an application talking to another application. So this is really a big part of a transport layer operation to be able to connect different applications. And I might have two SSH connections open on Sloop at the same time. And if that were the case, then what's going to end up happening is I would have a port number for one and a port number for another one. But they're both going to go to Sloop's port 222. So by reusing the destination port, I can actually have multiple connections to the same remote server. And what this does, and this is a really important idea, is it allows us to define any connection on the internet uniquely, completely, globally, universally, with 5 numbers. That's really, really hard to kind of get your head wrapped around. But these 5 numbers, we call it a tuple, is going to be the protocol. And our protocol is either going to be UDP or TCP. It's going to have the local address. So for example, it could be my computer and my port number. And then it's going to have the remote address. And it's going to have Sloop's port 22, right? And so there can only ever be this one connection. That, like, there's only my machine talking to Sloop would be the only one that shares these 5 numbers. It's actually kind of interesting. Let's do a little bit of math here and kind of diverge away. So I have a local address, and we haven't talked about IP addresses yet, but IP addresses are 32-bit values. So there can be 2 to the 32 IP addresses. Actually, there's fewer than that, but we're not going to worry about that. So I could have 2 to the 32 local addresses, 2 to the 32 remote addresses, and then 2 to the 16 source ports, and 2 to the 16 local ports, and then times 2 to the 1 for UDP or TCP. And if, of course, this is going to be a big number, but 2 to the 64 plus 2 to the 32 plus 1 becomes 2 to the 97. So the way the internet works, there could be at most 2 to the 97 connections between every computer to every other computer possible theoretically in the entire universe. That's a big number, but maybe not as big as we thought it was. I mean, but it's a big number. And it's interesting to think that there is actually an upper limit to the number of connections on the internet. Of course, in reality, these numbers are going to be far smaller. And so it's actually kind of interesting to think about that. But with this 5 tuple that completely identifies everything, these port numbers become really important as far as allowing 2 computers to talk to each other on different services, or having multiple remote computers talk to one server, or et cetera, et cetera. Port numbers are, as I said, they are restricted to just 16-bit values, and that gives us a range of 0 through 65,535. So it's actually 65,536 unique numbers, but we count 0 as a number. The first 10,024 numbers are reserved. These are the well-known ports. And one restriction that comes out of this is on Unix systems, you must be a super user to open up those ports. So if you see a service that's not in the first 10,024, understand that any user on that machine could theoretically run that service. RFC 1700, we've looked at RFCs before. RFC 1700 lists the officially assigned well-known ports. So before, when I said that the web server was port 80 and SSH server is 22 and the mail server is port 25, those are defined by, or in this RFC 1700. So the local port gets assigned to a connection when that socket is created on the local machine. And when we go to connect to a remote computer, our application is going to say, I want to connect to that remote server on this port number. So when I say I want to, if I'm on my PC and I try to open an SSH session to Sloop, my computer is going to pick a local port number from one of the available ports, and the remote port number is going to be the connection that I'm trying to establish to. With the fact that the ports are well documented and well known, what this allows us to do is to understand like what servers would be living on certain port numbers. So that way, if I want to connect to a particular service, I only need to use a host name. So for example, when we send email to each other, the reason why I can send email at just a regular computer internet name is because everybody uses port 25 for email. If that weren't the case, if everybody could just pick a different port number for their email service, then when I send email, I'd have to somehow put the port number in my email address, and that would be really weird. So we don't do that. We just require that all email lives on the same, all SMTP services all use the same port number. Likewise, when we connect to Sloop, it just defaults to using port 22. Now, SSH is a weird one because I can actually have SSH connect to a different port number. So for instance, you could do SSH-P. A common one is like 222 or 2222. And then go to a host name. Why? Because it helps us hide the service. And so a would-be attacker might not look at port 2222 to find an SSH session. I actually saw somebody many years ago, what they did is SSH was turned off by default. And if you sent us a particular certain ping packet to a machine, it would trigger an event on that machine, and then it would bring up SSH onto another port number. And then the SSH server would listen for about 15 seconds, and then it would terminate if nobody connected to it. And so you had to do something kind of out of band in order for the system to start the SSH server and make it available. And what that was trying to do was defeat this idea of automated service discovery. So the SSH server isn't there, so it's not listening for incoming connections, and nobody can scan for it, so it's effectively not going to show up in any automated scans. But if we do this two-step thing, we do something that somebody wouldn't normally do to kick off the server and make it start just for a few minutes, then we can log into that machine, but it's not going to be something that anybody would be able to just do. I'm not saying we should, I'm just saying it was a novel approach to protecting a machine from service discovery. So, let's talk about service discovery. So we can do a service discovery by running a command like nmap. And nmap stands for network map, and we can give it a machine or a range of machines, and what it's going to do is it's going to try to one by one connect to a machine, and then starting at port 1, it's going to open a connection to port 1 and say, did that work? If it didn't work, then it'll go to port 2. If it went to port 1, it's going to see if it can identify any well-known services that live on port 1. So for instance, if it gets to port 22 is typically going to be an SSH server, and nmap has some built-in rules for what happens when you connect to a port with an SSH server. And so what will end up happening is it will I'll check to see if it acts like an SSH server. And if it doesn't act like an SSH server, it'll see if it acts like anything else that it knows about, and then it'll tell you, oh, well, port 22 is usually an SSH server, but this thing's acting like a web server. And so Nmap is really useful for just kind of finding services that are available. It's good if we are, say, systems administrators and we are trying to figure out who all the email servers are, or whatever the service is. On the other hand, it's also really useful for hackers. Hackers can scan a range of hosts and use that to find SMTP email servers or web servers that are hidden. A really common thing is we'll have testing web servers set up. And if I'm trying to attack a domain, what I might be able to do is, if I can get access to the juicy bits behind the network security, I can use Nmap and see, are there any databases that are up for testing. A lot of times testing either has full databases, copies of databases, or they have stripped down databases that don't have all of the good security bits turned on, and so they become really soft targets. And so Nmap is a really useful tool. As I'm doing my lecture, I'll lecture, but when I go back to edit, I'll try to put in an example here of using Nmap. And if I don't, shoot me an email and remind me to do that. So we've talked about UDP a little bit. UDP is absolutely a minimalist transport protocol. The application creates sockets, and then it sends those protocol data units into the transport layer. The UDP is going to wrap source and destination port numbers in those two ID fields to send over the network. UDP lacks any persistent state in the transport layer. There is absolutely nothing about things that had to happen before UDP packet is sent, or things that happen afterwards. So this is really ideal for those kind of low latency kinds of things, which we'll take a look at. Because UDP lacks any persistent state, means if the application cares, the application needs to keep track of that state. So the goal of having it be transparent may not be achievable with UDP if the application needs that state tracking. So for example, if the application is concerned about keeping track of the number of users that are using a media server, then maybe UDP isn't going to be the right choice. So let's explore that for just a quick second. So let's say that I have a media server and I'm sending out UDP packets to all of my users. And I want to know how many users am I serving, or how many, I'm Netflix, I want to count how many people are watching the latest, greatest, whatever the show is. And I can keep checking to see how many UDP packets am I sending, but unless, like if I'm just throwing them out there, I'm not going to be able to say, well, what if the user is disconnected 10 minutes ago? I'm still sending out packets to their IP address and they're just getting dropped. I won't know. So what UDP says we're going to have to do if we want to use UDP is periodically the client is going to have to send a message that says, send me the next 15 seconds of video. So then Netflix is going to send us the next 15 seconds worth of packets, and we'll buffer those onto our machine. And in the meantime, Netflix is going to keep track and say, yep, this is an active connection, at least for the last 15 seconds. If I don't get another request in 15 seconds, then we're going to assume that the user is disconnected, and I'm going to not count that connection anymore. Likewise, this guy maybe hasn't sent anything for a while, so once that 15 seconds is timed out, then we're not going to count that user. But there's a really good example of how, if this was TCP, when the user disconnects, I would know about it. And I could close the socket and terminate the connection myself, kind of right away. So I could even tell you how long they were up, not just 15-second intervals or whatever set time we chose, but the exact instant that I got the message that they were closing their connection. So UDP doesn't do that. UDP makes the application build that state information itself. But it also then allows the application to carefully control how that state is tracked and what it means, and we're not depending on the operating system or the TCP kernel to do that for us. The application is in complete control over everything. In the case of UDP, we may have out-of-order delivery of messages. So think about your Netflix video stream. If you're sending out 15 seconds of video, that might get turned into a couple thousand UDP packets. And as those packets arrive, maybe a couple of them got dropped, or they're going to come in out of order. And is it a big deal? Well, if a packet is only one frame of video, there's maybe 60 frames of video per second. So you drop a frame and then you keep on displaying things. The human eyeball is not going to notice that. Yeah, okay. People say they need 120 hertz screens and things, but really we stop seeing any real difference once we get past about 30 frames a second. So with that in mind, out-of-order delivery in UDP may not be a big deal if the application doesn't really demand it. On the other hand, if you're doing this with something like a database and only half of our transactions are arriving at the database server, that could be really disastrous. Imagine the ATM network using UDP packets. Sure, I'll let you withdraw $1,000 from your bank account, and I'll tell the bank server that I gave you $1,000, but if that message never gets to the bank, I won't know that, and the bank won't know that you took $1,000 out of your account. And very quickly, we'd be going bankrupt. So again, and that kind of gets into the missing delivery thing here. The other thing about UDP is there's no built-in breaks. Because it's so minimalist, it could just flood the network, and it could inject more packets than what the network layers can handle, and then they just start dropping left and right. And then that's going to cause missing deliveries and all kinds of chaos. But there are some clear advantages. Like I said, the application often knows more about how to deal with clients than the network stack does. I mean, if you think about it, Netflix is new and it has the latest information about how it should do things. TCP was developed in the 1960s and for purposes that have nothing to do with live video streams. And so it's really tough to argue for modern applications depending on 1960s technology to do their data delivery. Hopefully the application would know better about how to control those data streams than TCP would, for instance. Maybe it does, maybe it doesn't. And we'll take a look at that as we go along. Other advantages absolutely can be low latency. Because I'm not using any extra packets, everything I send is data. And there's very little overhead on top of that. And so for high performance local connections, UDP can really run circles around TCP under the right scenarios. Low impact on the server, because if we don't need all that connection tracking, if I don't need reordering, if I don't need connection tracking and missing delivery tracking and stateful tracking, then UDP is the thing. Much lower impact on the server than TCP. And finally, the big thing is the application can define exactly what it needs and can build it itself without any of the extra overhead that TCP brings in. So from that perspective, UDP is the minimalist approach to things. And I always try to put pictures of things, metaphors on my slides. I wanted to just explain the metaphor behind this one. This is minimalist art. And, this is exactly the UDP approach. You have exactly what you need to get the message across and nothing more. And if you happen to understand what the artist was trying to say, the message was delivered. If you do not understand what the artist was trying to say, then the meaning is lost. And that's exactly how UDP works. And so I think the samurai picture here is less important as the concept of the metaphor of minimalist art. The UDP segment includes a checksum, and the checksum includes, and so this is really weird to have to admit, but we always talk about how in an encapsulation environment we never look into other parts of the protocol layer. Well, this is one of those times that we break that rule. So this is what's called the pseudo header format. So these are borrowing fields from the whole TCP message. Well, I'm sorry, UDP IP message. So this is, the addresses are coming from the IP, not UDP. So this is stuff outside of the UDP header. Zeros in protocol come from outside the UDP header. UDP length comes from the envelope header. So this stuff comes from lower in the hierarchy, and that breaks one of our rules. But it is what it is. Sometimes the academic purity of a rule can afford to be broken. And in this case, what UDP is trying to do is it's trying to prove that the packet was received without any data errors. So it makes sense that we're going to include things like the address of the sender, the address of the receiver, the verification that this is really supposed to be a UDP protocol and not some other randomly garbaged up message that just happened to have bits set to make it look like a UDP message. And then what we're going to do is we're going to use the header of the UDP message, and we're going to then use the data, and we're going to compute a checksum, and that checksum is going to be stored in the UDP header. It's the last field of the UDP header. The checksum is then used during sending to send the message. So we'll initially start with the destination or the checksum being 0. We'll run the checksum algorithm, we'll get the number, and then we'll fill it in before the packet gets put into the data layer, the network layer. The checksum algorithm, again, this is stuff that was developed in the 1960s. It has to be really, really simple because the hardware back then was really, really simple. What we're going to do is we're going to add up 16 bits at a time. And as we get carry, we're going to wrap the carry around so that a carry bit in the 17th position gets added into the next addition. So if you think about what we're going to do, we're going to take two 16-bit numbers and we're going to add them together, and we could get a 17-bit number, right? So I'll have 16 bits plus a possible carry. And in fact, if I just do these as 32-bit numbers today, if they're 32-bit numbers, the first most significant 16 bits are all going to be zeros. So what I can do is add these things up and then take the upper 16 bits and add it to that. That's going to be a 0 or a 1, right? So it doesn't have to be as weird as this wraparound thing says. There's just no clean way in English to describe what's going on there. And finally, what we're going to do is we're going to store this checksum in one's complement. And in particular, what we're going to do with this one's complement is if the number ends up as being zeros, we're going to negate it. Because 0 is used as a placeholder for no checksum. So as an example, what we have is a Wireshark capture of a UDP packet. And we said that the IP addresses are going to be used in this pseudo header. So if we look around here up at the Internet Protocol, I see source and destination addresses. And they're going to be stored, I guess, there in hexadecimal. So my first 16-bit value is going to be the C0A8, and then the next 16-bit value is going to be 0684, and if I add that on, I get C72C. The next 16-bit value is C0A8, and if I add that, I get 187D4, but then that's the carry, so it gets wrapped around. I then add the 0620. 0620 was the last part of the IP address. So the running checksum at that point would be 8DF5. The next thing is going to be the protocol, which is 17. And if we look, there's the, nope. Yep, there's the protocol. They're just kind of in a weird order. So there's the protocol that takes my running CR, or this should be checksum, not CRC. Takes my checksum up to 8E06. 58 is the length of the packet, which was the 74. And we should be able to see 58 in here in the hex somewhere. Scanning for it, I don't see it. I hope I didn't mess that up. I don't see it. Well, all right. Anyway, we'll keep on going. Source port, destination port are all going to be in here, and then we're going to start getting into the data. Anyway, all of this gets checksummed together, and the resultant hexadecimal comes out to 71C3, and then we take the ones complement, where we invert all of the bits. So remember, 2's complement is you reverse all the or invert all the bits and then add one. We're not going to do the add one. This is just the 1's complement. And if we look in here, sure enough, there is the UDP checksum. Now this is saying unverified because apparently we're not validating the UDP header checksums. So I don't know if that's a thing that maybe just because I'm under Windows it didn't do it, or it's a Wireshark setting that didn't do it. But it should verify it. That way we know that we didn't receive it in error. So that checksum can handle if, like, so let's just say, for example, 1 bit arrived wrong. So instead of this being 8, it was 9. So because this is 9, this then becomes D, and everything else after that ends up being a different number. I think it's just off by 1, so it should end up being 4. And then when we negate it, it's not going to be right. And so if even one bit arrives in the wrong position or the wrong value, the checksum's just not going to match. So let's take a look at a couple applications that use the UDP, and one of them is the domain name system. Now we've seen this earlier when we looked at different kinds of internet service providers, and the DNS was a pretty important part of that. But the DNS is a really interesting system because the UDP message itself fits, or the DNS request fits inside a UDP request. And so there's no need to have multiple PDUs. What happens is your DNS server sends one PDU to the remote DNS server. The DNS server responds with one PDU back. There's no ordering problem because everything fits into one PDU. There's no arrival out of order problem. There's no nothing. If, for instance, I send a request and I don't get a response, I just try a different DNS server, or I can send the request again. And so this allows DNS to be very low latency. It also allows the servers themselves to be much simpler, and that way they can handle much larger amounts of incoming traffic. So if I had to maintain the connection status of all of the connected clients, the DNS server could easily get overwhelmed with the tracking of all of the different connections, and this is just a time where the application itself knows better. And UDP is a perfect choice for this application. Another version of this, another version of a protocol that works really, really well would be a file server. File servers they're often implemented as either TCP or UDP, but a file server can use UDP. And imagine, for example, that you had to apply the image to all of the lab machines. So we have one master copy of a lab machine, and we're going to distribute all of that data to 30 or 40 computers all at once. What I could do is I could have the imaging server send out UDP broadcast messages, and we could broadcast all of the messages out to all of the computers at one time. And so I send out this broadcast message. Every computer sees the same message, and it says, yeah, I'm interested in that chunk of data. And so it'll receive its little piece of data to be written out in the hard drive. And then it'll just kind of locally keep track of what data it's received. Once it's done with the broadcasting, then the imaging server could come back and say, okay, so now that we've done all of the bulk work using broadcast, I didn't get block number 50. Can I have block 50? And another machine might say, well, I didn't get block 80. And another machine is going to ask it for block 200. But it's going to be a lot more efficient to service those individual requests than it is to have 40 computers individually transferring blocks at a time in parallel and saturating all the networks and lots of network traffic to keep track of. So in this case, it can be faster. But the application is hinged on the fact that we're going to use this broadcast technique. If I don't do broadcast technique, then all bets are off. So for the right workload, UDP has some interesting advantages. I didn't have a slide on it, but let's take a look at a web server. Web server maintains connection. So once I've opened that socket, I keep that socket open, and we send data, send a request, get a response back. I send data, get a response back. I send data, get a response back, and then I close the connection. That's supposed to be the word close. Close. And in this environment, because I want to exchange data and kind of remember where I was, it makes sense to allow the web server to hold that connection open. And so the web server is going to hold the socket open, and it's going to depend, so the application is going to keep the socket alive. And then we're going to depend on the OS to actually implement that, or the networking kernel. And in fact, it's the overhead of creating a web connection is actually fairly high compared to, say, the DNS, where I just throw a DNS request and I get my result back. Here I have to negotiate, I have to do all the TCP stuff to get that connection opened, and then what ends up happening is the connection has a high latency. So we'll leave it open. If you connect to a web server and you request the page, it's likely that page has some images, so you're going to want to request those too. So we're going to just keep this thing open and let you keep requesting all of the data that you're going to request, and then we'll even keep it open for some period of time thereafter. And so we'll do this thing called keep alive, where your client can periodically send a message that says, Yeah, I'm still on the page. I might be requesting more stuff from you, and since it's relatively expensive to create a network socket, let's keep this connection, this line of communication open. And as a consequence, the web servers all use TCP. Like, this is absolutely TCP's ball game. This allows the web server to be a lot more efficient, because the web server no longer needs to do things like make sure that I have a coherent string of data going back and forth. The network layer or the transport layer can do that. The transport layer can make sure that if I send a gigantic string of text, that I receive a gigantic string of text on the remote side. UDP, I could send a gigantic string of text, but it could arrive all jumbled, or parts of it missing. So this is really the difference between a good classic TCP kind of application, where we want that reliability and that ordered property of the transport layer, versus UDP, where I really need the high latency, and if it doesn't work, we'll figure it out. So this is actually a good stopping point for the first part of this lecture. So I'll go ahead and end here, and then we'll pick up again with part 1B, where we look at an overview of TCP.